Hi everyone, we're going to pick up where we left off last time. Now we're going to talk about descriptive statistics. Descriptive statistics being talking about measures of center, and measures of spread are the ones we're going to talk about. Okay, and the R file I am looking at is the same one as last time, just the second part of it. We covered the first part in the last video, now we're covering the second part. So measures of center, different ways we can talk about, the center of data. We could talk about something like the mean or the median. Those are the two popular ones there. And for a measure of spread, we have the popular ones being standard deviation, variance. We can talk about the range. We can talk about the IQR, which is interquartile range. There is something called the mid-range. There's lots of ways we can talk about here, and this is only a few. Mid-range. And the way we would find all these, for example, the mean. The mean is usually denoted with an X bar or the lowercase Greek letter mu. Are two ways you could label that. Standard deviation you'll see as an S or a lowercase Greek letter sigma. Variance is usually an S squared or a sigma squared, right? Because standard deviation, if you want to find that, you can just square the variance, or vice versa, find the variance and then take the square root of that to find your standard deviation. A mean is in a pretty simple calculation. You add up all of the values and divide by the total. Add up all values. Then divide by the total. Or not the total, divide by the number of values. And I'll go ahead and I'll move this piece down. So here in R, I have some data set up. I have it called Verizon. These are phone network download speeds in megabits per second. So this is the data that I have. I'll click run. So now I have this data saved as Verizon. So whenever I refer to Verizon, it just pops up all of that data. And if I wanted to calculate the mean here, I could just simply use the mean command and get 30.74. So if I did that by hand, it would look like this. I'll move this again. If I wanted to calculate this mean by hand, how you would do it is you would add up all of these values. 38.5, 55.6, 22.4, 14.1, 23.1, and then you would divide by however many numbers there were. So there's 1, 2, 3, 4, 5. So we're going to divide that by 5. And that is how we get the mean. So this all equals to 30.74 here. If we wanted the median, how we do that is we sort least to greatest. Sort least to greatest, and then pick the middle value. I'm going to move this all. Pick the middle value. Or take the average of middle values if there's a tie. So if your list of data has an even number of observations, an even number of data points, then you'll always have one that's in the middle. If there's if there's an odd number, you always have one that's in the middle. If there's an even number, then when you sort least to greatest, there's going to be a tie. So let's see what these numbers are if you sorted them least to greatest. So if we were to do this by hand, we would sort least to greatest: 14.1, 22.4, 23.1, 38.5, and 55.6. And then the median would be the one in the middle. So if I wanted to just use R, I could use the command median, and it'll give it to me, 23.1. Right. This one's not bad to do by hand because the data set is small. We can do the mean and median of that by hand. It gets a lot harder if the data set is larger to sort it all by hand, which is why software is great. Okay. So those are different measures of center and spread. One is more of a numerical calculation. The other is more sorting. And notice, if these numbers got any bigger, this wouldn't change. If these numbers got any smaller, this also wouldn't change. So the median is more stable in that sense, that it doesn't matter what the values are, the higher and lower values. If you change them, the median won't change. But if you change any of these numbers in the mean, then certainly your mean will change. So your mean is more sensitive to changes in your data set than the median. So take that into consideration when you decide which measurement to use for whatever reason. If your data is very skewed one way, maybe the mean doesn't make much sense, but maybe the median makes more sense. Or if you have a lot of outliers or very, very high or low outliers, then that will impact the mean a lot, whereas the median won't be affected regardless of how high or how low the outliers are. Standard deviation is a measure of spread. Okay, so actually let's go backwards and start with variance. I apologize, you might be hearing my neighbor cutting their lawn with their lawnmower, so if you hear that noise in the back, that's what it is. Where did this E come from? I don't know. So, say we wanted to calculate variance. So, to calculate variance, we use the formula. We use this is a capital Greek letter, sigma, right? This is a lowercase sigma. This is a capital sigma. And what it represents is sum, right? We're going to add up everything I put inside of it. So we're going to add together every data point minus the mean, square it, and then we're going to take that whole thing and divide by 1 minus the sample size here. So the sample size in this example is 5 because there's 5 numbers. 1, 2, 3, 4, 5 numbers. So the denominator here would be 4. And then if you wanted the standard deviation you can kind of tell by the symbols. To get from this symbol, or to get to this symbol from this symbol, you take the square root. So if I were to calculate variance by hand for this problem, it would look like each value minus the mean. So 38.55 minus the mean squared plus, and I would do that for all of them, 23.1 minus the mean squared, and then all of that divided by 4, because there's 1, 2, 3, 4, 5, and then this is n minus 1. So your variance will be whatever that is, and your standard deviation is the square root of that. So to calculate standard deviation, we can use the command SD to get 16.45488. And you can check if you took the variance, you'd get that. And if I took the square root of the variance, see, if I take the square root of the variance, I get the standard deviation. Right? So those are related via squaring and square roots. And variance and standard deviation is a measure of spread. It measures how spread out your data is. If you look at what the formula is doing, what this is doing is it's measuring how far is the data points from the mean. How far are the data points from the mean? So what this is kind of looking at is what's the average distance of all of the data points from the mean, is kind of what this is looking at. Now, it's kind of hard to compare one standard deviation to another between two sets of data because they could be on completely different scales. For instance, if I was talking about the height of people, right? We're talking, in terms of inches, maybe anywhere in the range of, for adults, maybe 50 to 80 inches. That's not that large of a range. Whereas if I was talking about the variance of that compared to the variance of, say, house prices are in the hundreds of thousands of dollars, and the price between two houses could be in the tens of thousands or even hundreds of thousands of dollar difference, right? So the variance is going to be a much, much, much bigger number just because your data points are much, much larger numbers. So the way we kind of compensate for that is with this thing called coefficient of variation. And what coefficient of variation does is it helps to compare two things on the same scale. For instance, your standard deviation, if we're talking about heights, this is going to be relative to that and then divided by the mean, which is also relative. But if we're talking about housing prices, your standard deviation, again, is going to be very large, but then you're going to be dividing by a very, very large number, so it helps scale it down to be comparable. So we use this thing called coefficient of variation, and that's so that instead of comparing the standard deviation of two data sets directly to each other, that may not make sense, right? To talk about on average is one more variable than the other, right? We wouldn't know because they're on different scales. So we divide by the mean to get them onto the same scale. And this is a better measurement to compare two data sets with. Moving on, we still have a few things on this list we need to work through, being the range, the interquartile range, and the mid-range. So I have another data set here. Again, data speeds. This is just a larger data set. Again, we've seen how we can calculate the mean, the median, the standard deviation, coefficient of variation. That's all the same, right? And we can do that very quickly. The next one we're looking at is the range here. So range is pretty straightforward. This is the biggest, minus the smallest, your max minus the min. So there's a few ways you can go about doing that. You can look at the minimum in your data set with the command min, and you can look at the max with the command max, and you can look at the range. So the range here is 77.8 minus 0.8, which is 77. Okay, that's one way you could do it. There's the command range that will give you both the min and the max at the same time. Instead of looking at the min and max separately, you can use the command range and it'll give you both of them. And if you wanted to calculate, you could do max minus the min in one line. That's one way you can calculate the range. Here the numbers are easy for us to subtract in our head or even on paper, but here's one way we can do that. Just type out the max minus the min, right? Without knowing what the numbers are, you can certainly command them with max and min. You could say, notice when we typed out range, it gave us two numbers, right? It gave us a first number and a second number. And remember on the first day when we did an introduction to R, we could talk about how to extract certain numbers from a vector or a list with these brackets. So bracket 2 will give me the second thing in the list. Bracket 1 will give me the first thing. So what I'm doing here, I'm saying, okay, I want to take the range and I want to take the second number minus the first number. And that will also give it to me. Or you could use this command diff. That'll look at the difference between the values. So it'll look at the difference between these two values in the range. All valid ways to compute the range. I like this. I feel like this one is the most intuitive, the easiest to understand out of them all. Just a simple max minus min, and then we're done. There are other ways to do it depending on what your preference is. I think this is the easiest to understand. And now we're getting into the 5-number summary stuff. Before we do that, one more thing to add about the range is this thing called mid-range. Mid-range, so range gives you the difference between the max and the min. Mid-range gives you the average of the max and the min. So if I wanted to do the mid-range, right, think about what mid-range means. It's the middle of the range. So it's the average of the min and the max. The average finds what's in the middle. We could do max of data speeds plus min data speeds divided by 2. Could do that. Or we could just simply do mean of the range. Oops. Data. You know, either one of these will work. So when your homework asks for mid-range, this is what they're asking for. The middle of the range. What is in the middle of the data set? I put it down here with measure of spread because it kind of went along with range, but really this belongs better up here with measure of center. Right, because it's measuring what's in the middle of the data set. We have the median as one way, the mean as another way, and then the mid-range as another way. Next, on to the interquartile range, or the 5-number summary. We have something called the 5-number summary. The 5-number summary incorporates 5 values. The minimum. Let's list this in order. The min, the first quartile, the median, the third quartile, and the maximum. Okay, so quartiles think quarters, 25%. So your min is 0% of data is smaller than this. Right? Nothing is smaller than your minimum. Here, your first quartile, and you'll often see this written as Q1 for first quartile. 25% of data is smaller than this. Right, we're going up by 25s. Your median being 50%. 50% of data is smaller than this. Third quartile you could see as Q3 being 75% of data is smaller than this, and your max being, all of your data is smaller than that. Right? Everything is less than your max. And I say smaller than, or equal. Smaller than or equal. So this is your 5-number summary, and these are values that create what's called a box plot. So let's look at that. So to calculate these different, these are called percentiles or quantiles. It doesn't have to be a multiple of 25. Right? It doesn't have to be a multiple of 25. Here I have 0, 25, 50, 75, 100. It doesn't have to be like that. It could be anything. For instance, median we know is the 50th percentile. Right, 13 point. I'm actually going to clear this over here. We can look at the 25th percentile. Right, so if I was doing this example, my min is, what was I already forgot my max and my min. My min was 0.8. My Q1 is 8.4. My median is, right, I got 8.4 from first quartile. My median is 13.9. My third quartile is, that's my 75th percentile. So the command I'm using is quantile. Quantile, specify your data set and then what percentile you want to look at. First quartile is the 25th. Third quartile is the 75th. 21.4. And then the max was 77.8. Okay. And these, like I said, don't have to be multiples of 25. You can calculate any percentile you want. So if I wanted, the 90th percentile, we'll call it P90, that would be 34.99. If I wanted, say, the 45th percentile, we'll call that P45, that would be 13.12. That we have there. And these numbers, these are the numbers that make up the 5-number summary. They're used to make a box plot. And 2 of these values, Q1 and Q3, make up your inner quartile range. So your inner quartile range is Q3 minus Q1. And what that's going to be used for is calculating outliers if there are any. So we have these 5 values, min, Q1, median, Q3, and max. We could calculate them, all one by one in all these different lines, or we can use the summary command and we can get all of it at once. So if I use the command summary, it gives me the min, the first quartile, the median. It gives me a bonus. It gives me mean. Mean is not a number in the 5-number summary, but the summary command does report that. So if you're asked to give a 5-number summary, you do not include the mean. It also gives you the third quartile and the maximum. And now interquartile range is your third quartile minus your first, so 21.4 minus 8.4. So 21.4 minus 8.4 is 13. Here. And we're going to see how we're going to use that to make to calculate outliers. So to make a box plot, here's how it goes. So we have kind of an axis here that we can label. We're going from 0.8 to 77.8. So we're going to have to label the axis accordingly. So I'll start at maybe 0, and I'll go 10, 20, 30, 40, 50, 60, 70, 80. Okay. And we start plotting these. So my min is 0.8. So at 0.8, I'm going to make a little dot, right? You know, if I dropped it right down, that would be 0.8 right there. My first quartile is 8.4, which is about right there. So if I dropped this straight down, I would get 8.4 right there. Median is 13.9. Okay, so I'll make another point there. My third quartile is 21.4. So I'll make a point about right there. And then my max is all the way out here at 77.8. So it's very, very far out. And then to make a box plot, we put a box around, we put a box around our first and third quartile. And we put a bar down through the median. So that's the box, right? Some people call this a box and whisker plot. Right, so this is a box plot. And what the whiskers would be is you connect the box to the min and the max. Okay. So notice, you know, we have so much going on over here, right? That's a very large jump. Let's see what this plot looks like when we make it in R. So I'm going to use the command boxplot. And my windows are kind of cramped up over here, so I'm going to drag them out a bit. Sometimes when you make a plot and there's not enough room to display it, it'll give you a warning or an error message. So I'm going to run this box plot. I'm going to hit Control Enter, and this gives me a box plot. And I can, by default, it gives you a vertical plot, but I can add this argument to make a horizontal plot instead. Add this piece saying horizontal equals true to make it a horizontal plot. And we see this plot here, okay? And look what we have. We have the bar is not, the whisker here, this arm is not going all the way out to 77.8 like we have drawn in ours over here, right? It has these kind of isolated points and it stops the bar here. What R is doing here is it's making what's called a modified box plot, right? It's making what's called a modified box plot. What a modified box plot does is it calculates if there are any outliers and it plots the outliers separate, right? So notice if you ignore all of these points and look at just this on its own, right? You know, kind of whisker to whisker. it looks a lot more balanced and symmetrical, whereas the original one did not look symmetric at all. We had this point going this arm going very, very far out over in this direction. So how do you calculate these outliers? So that comes with your interquartile range. So our interquartile range, to calculate outliers, we calculate two values. We look at your first quartile minus 1.5 times your interquartile range. And you look at your third quartile plus 1.5 times your interquartile range. Anything smaller than this value is an outlier. Anything bigger than this value is an outlier. So let's calculate this. So my Q1 was 8.4. So my Q1 was 8.4 minus 1.5 times my IQR was 13. And then Q3 is 21.4 plus 1.5 times 13. Let's see what these two numbers are. I'm just going to use R to calculate this real quick. 8.4 minus 1.5 times 13. Okay, and I'm going to hit the up arrow. When I'm down here, I can hit the up arrow to edit that, or to redo it. 21.4 plus. So anything less than negative 11.1 and anything bigger than 40.9 will be considered an outlier. So let's take a look at the data. So we can use the command sort data speeds. Notice there's no value less than negative 11.1. So in my box plot, in this box plot here, there's no isolated points to the left. But let's look at points bigger than 40.9. We have a few, right? We have 43, 55.6, 71.3, and 77.8. And notice where these points are. 43, 55.6, 71.3, and 77.8. Those are the outliers. So a modified box plot accounts for those. So a modified box plot would be like this. You know what I'll do? I'll copy this. Copy. Okay. So my highest one that's not an outlier is 38.5, which is about here. And then outliers at 43, 55.6, outlier at 71.3, and an outlier at 77.8. Okay. So these are outliers, values that are, abnormally high or abnormally low in your data set. And calculating outliers is one way you can do that. There's another way you can calculate it. They're not exactly the same, but you may come across problems asking for calculating significantly high or low values. And one good rule of thumb to calculate this is to calculate the mean minus 2 standard deviations and the mean plus 2 standard deviations, 2 times your standard deviation. Okay. Anything less than this being considered significantly low, and anything Sorry, did I say that correctly? Anything smaller than this being significantly low, and anything larger than this being significantly high. Is another way to calculate significantly higher low values or identify significantly higher low values. The cutoff is not necessarily going to be the same as IQR. It's not going to be necessarily the same as the cutoffs it gives you here, but it is another methodology of identifying these kinds of points. Okay. We could add a color to the box plot if you wanted to. Color is green. Just to add a little detail if you wanted. You could also make stacked box plots. So I'm going to go ahead and enlarge this now. We're done for now with the written notes, so I'll enlarge this. I'll clear this too. R has some data sets built into it that we don't have to read in at all, that are just native and built in. One of them is called Beaver 1. Beaver 1 and Beaver 2. And if there's ever anything in R that you want to know something about, you could use the question mark command. For instance, I'm going to look up information about this Beaver 1. So when I run that, it'll bring up all documentation R has on this data set. It's from 1994. It looked at temperature dynamics of beavers in Wisconsin. Has 114 rows and 4 columns. It has all of these variables and so on. Say you wanted to know more about how the command boxplot works. You could type question mark boxplot, and R will give you all of the documentation it has on it, and it tells you everything you could put in here. It describes what all of these different things you can plug in is. It gives you some examples that you could run for yourself. You could copy paste to run different examples and try different things. So this saves you a Google search, basically. If you try to type in how to do something in R or something like that, a lot of times it'll take you to the documentation, which we can find inside of R without having to look elsewhere. So that's a nice little thing to keep in mind about, is the question mark command. It can be handy. So back to this beaver data set, we're going to look at beaver temperatures, right? And let's see what this data looks like. The command head will give you the first few entries of the data. So instead of us typing out the entire data set to see what it looks like, it could be a lot. What we can do is just type the command head to look at the first few, just to get an idea of what we're looking at. So we have the day, the time, temperature, and whether or not they were active. And again, it describes all of that here. The day, the time of observation, the temperature, and an indicator whether they were active or not. And then same thing for Beaver 2, question mark Beaver 2. It brings us to this same documentation, right? And then we can look at the first few entries there. Notice days and times, temperatures are all different, and then whether they're active or not. If we displayed the entire data, some of these would be a 1, right? So some of them are a 1 indicating that the beaver was active, 0 indicating that it was not active. Okay, that's not really important for us. But what we can do is we can plot 2 box plots together in the same plot and compare them. So I can use the command boxplot and then type in what I want to make a box plot of. I want to compare Beaver 1 and Beaver 2. And remember, whenever you want to, let's look at head again. Whenever you want to specify a specific column in your data set, you have to use the $sign, right? So I'm looking at the data set Beaver 1. I specifically want to look at the temperature column. So you specify that with a $sign. And then similarly for the Beaver 2, I want to look at the Beaver 2 data set, specifically at the temperature column, so use $temp. And then I'm saying I want this to be a horizontal plot instead of vertical, and then if you wanted to add a color, you can. And we can see this stacked box plot and make comparisons between the two. For instance, it seems like so this would be beaver 1 and beaver 2, right? 1 and 2. It seems like the body temperatures of beaver 2 data, I think the difference is beaver 1 was in November and beaver 2 was in December. That in December the temperatures were a lot more variable, right? We see the range is much wider. The interquartile range is much wider. Okay. And overall in November, the body temperatures were lower than the body temperatures in December, right? Your min, well, we have some outliers here, but ignoring those, your minimum is smaller than the minimum. First quartile is smaller. Your median is smaller than here. Your third quartile here is smaller than the one here. Your maximum here is smaller than here. Even considering the outlier, the maximum is lower, right? So the body temperatures are overall lower on these days than they are on these days. So again, I think it was beaver 1 was November temperatures and 2 was December temperatures. So overall temperatures in November are lower in beavers than in December. But in December, not only are they higher, they're a lot more variable, right? Your range is much higher, interquartile range is much higher also. So the data is a lot more variable or a lot more inconsistent in December and more consistent in November, although the temperatures are lower in November. So this is how we can plot box plots side by side and start to study them and make comparisons. Now, with all of this, you should be set to work on the next homework. I believe it's homework 3. So you can get a start on that. And of course, please do email me any questions you have while working on that. All right. Have a good day, and let me know if you have any questions.